Okay. This might look like all over the place, it's not that structured because I just got to get through some of this stuff fast, okay? So, let's talk about, we talked about ionization energy. Did we talk about electronegativity?
Yes.
Yep. The highest electronegativity is for fluorine, yes? Covalent bonding. There is two types of bondings. There is one called covalent, and the other one is
Ionic.
ionic. I have already mentioned some of this before, yes? Covalent bonds is when they share electrons, and electrons are shared most of the time with what elements?
Non-metals.
Non-metals with non-metals will give you covalent bonding. Ionic bonds are those with a metal with a non-metal. Specifically, there are numbers to calculate this. And the numbers are, if the difference in electronegativity is from 0 to 0.4, I did give you an electronegativity table, yes? I mean, I told you that one exists? No. Whatever. So, if the difference in electronegativity, they're numbers, okay? For the electronegativity on the periodic table. Fluorine is the highest one with a 4.0. Then comes oxygen with a 3.5. Then comes nitrogen and chlorine with a 3.0. Carbon with a 2.5. And hydrogen with a 2.1. Okay, those are the most important ones. Okay, if the difference in electronegativity between them is 0.4, this bond is called nonpolar covalent.
Non-polar covalent. Professor, repeat that one more time. What's a non-polar covalent one more?
If the difference, don't worry, okay? The difference in electronegativity is from 0 to 0.4. This is called the nonpolar covalent. Difference in electronegativity. I'm going to show you now. Of course, I can't use 0.4, so from like 0.5 to 1.7, this is called, what is it called? Polar covalent. Outstanding. You guys got it. And greater than 1.7 is called ionic.
Very polar.
Yeah, very polar covalent. So polar covalent that it is called ionic.
Doesn't it go up to 4?
No, up to 4 is fluorine by itself. Okay? Now this is the difference in electronegativity of the bond, yes? So let's find this. The bond here in HF, is it called ionic? Is it polar covalent? Or is it non-polar covalent? This bond here, fluorine is 4.0, and this is 2.1.
Ionic.
Ionic.
Ionic. What's the difference in electronegativity between those two?
1.9. 1.9. The difference?
1.9.
Outstanding. Difference in electronegativity here is how much?
Good job, Baba.
Difference in electronegativity between those two bonds. It is carbon with 2.5, hydrogen 2.1. The difference in electronegativity is 0.4. So this bond is non-polar covalent.
Oh, so that's how you figure it out. Then you have to get the differences
Yes.
to figure it out.
You get the difference between them. Huh?
We'll be given a table.
You need a table, and I will give you a table. What you have to know is that fluorine is 4.0, oxygen 3.5, nitrogen and chlorine go together with a 3.0, then is carbon 2.5, and then hydrogen 2.1. Okay? I don't know if you noticed that they are decreasing by 0.1, yes? Except from carbon, hydrogen. Those are the most important ones, without knowing. So, when the bond is polar covalent, okay, there is a possibility, depending on the molecular shape, that the bond has a dipole, okay? So, they call this, what is the difference in electronegativity between these two? 3.5, 2.1 is 1.4. this bond here is polar covalent, yes? And this bond, because it is polar covalent, will have the one that is more electronegative will carry a delta negative charge. Is that delta?
No.
So that's lower.
Oh, that's change.
No,
Oh,
it's
it looks like a this.
It's lowercase delta. Capital delta is the triangle. Okay? So that is called delta negative, and this has to be delta positive. This is delta negative, or the electrons from this bond are more towards the oxygen because the oxygen is more electronegative. Yes? The hydrogen is less electronegative, so this side carries a partial positive, and this carries a partial negative charge. Okay? They are partial. They're not full negative and they're not full positive. So they're not ions. Okay? So this bond here has a dipole. And dipole means what? Di means what?
Two.
And poles means?
Polarity.
The obvious, yes?
Polarity.
Poles. One is positive and the other one is negative. Okay? Dipole. One positive, one negative. If it is a carbon with a hydrogen, this is not considered a dipole because it's less than 0.4. This is considered non-polar. Yes or no? Now the strength of attraction, whether the compound is ionic or not, depends on a law that looks like this. The energy of attraction between the two nuclei is equal to a constant charge of the first one, charge of the second one, divided by the distance. This is the distance between the two nuclei.
So this is to calculate what again? This one?
This is a force of attraction between the two elements that make up the bond. Which of those bonds is more polar? And you do not need a periodic table for that. Okay? I mean, you don't need the numbers for the electronegativity for that. Which bond is more polar?
Well, polar is fluorine.
CF, okay? Because F is more towards that side of the periodic table. This bond is more polar. Okay? Which one is delta negative and which one is delta positive?
Fluorine is delta negative.
Fluorine is delta negative and this is delta positive. Of course, carbon makes how many bonds? I explained this already before, yes? Carbon makes 4 bonds.
4.
Yes. Nitrogen makes 3 bonds because it has 5 valence electrons, needs to get to 8. Oxygen makes 2 bonds. Fluorine makes 1 bond.
1 bond.
All halogens make 1 bond. Could make, in general, make 1 bond. Okay. So now, the strength, write it down. The strength of the bond depends on the bond length. The reason it depends on the bond length is this equation here. The equation should not be like this. The equation normally, it will be r squared, okay? But if one element is different size from the other, that's why they put D here, because it's the distance between the two elements. So here is how it is. Have I done this before? I've never done this. The surgery went wrong. You like this one better, don't you? Done correctly, yes? The distance between here and here is called D, yes? It would be called, this is the radius, yes? Diameter is the whole thing and radius is? Hello?
Half of it.
Half of it.
Half of it.
But I can't write down here r squared, even though the equation in physics is r squared. I can't write it because this radio is not the same thing as this radio, yes? But you can still, okay. The force of attraction between these two depends on this distance, okay? If you live here and your boyfriend lives in Canada, how strong is your relationship?
Not very strong.
Believe
Not very
me.
strong.
Not very strong. Because distance messes things up. So, which one is further? That one or this one? This one has a longer distance, so which bond is weaker?
The one that you just did right
This
now?
is weaker. Okay? This is a weaker bond, and the reason for that is because the force of attraction between those two nuclei is lower because of the distance between them. That clear? So, what does this translate into? This translates into knowing the size of the elements, my friends.
Okay.
You know the size of the elements, yes or no?
No.
Relative.
So, in your opinion, which bond of those is weaker?
Oxygen is weak.
Which bond is weaker?
Oxygen?
Seriously?
I need the periodic table.
As you go down, it increases.
As it goes down, the elements get bigger, yes?
Right.
Yes,
The
that's what I'm
oxygen is on the top,
Yeah, I need some.
and the sulfur is on the bottom.
Sulfur.
So sulfur is weaker
Is that
and
clear?
oxygen is clear.
Sulfur is not weaker. Okay, sulfur is just sulfur, yes? The bond between sulfur and hydrogen.
This is
This bond is weaker. Why is this bond weaker?
Because sulfur is bigger.
there's a
Because
bigger
the bond
distance.
length, is bigger. And why is this bond length bigger? Because sulfur is big. Yes or no?
Yes.
Yes.
Outstanding.
Outstanding. Okay, very good.
You almost had it before me.
I know. You beat me to the punch.
Which bond is weaker?
Which one's weaker? Which one's bromine? Bromine is the bottom one.
Over here, no, as you go down the element gets bigger.
That's I.
Sorry.
So I.
Why don't you understand? Did you just get here?
Carbon and iodine.
No? Where have you been?
She's been here. She's been here.
Because I've been explaining this, why it's weaker for 15 minutes.
Okay.
Okay, I'm gonna repeat what I just said 3 minutes ago. You ready? This bond is weaker because this bond length is bigger than this bond length. Why is this bond length bigger? Because sulfur is bigger. Yes? Right here. If this is bigger, the bond length is bigger. So imagine that's oxygen and this is sulfur. Which one is
Iodine.
weaker from the top?
Iodine.
Who?
C. I.
Wow.
I don't know how
You
you
guys
say
take my breath away.
it. Outstanding.
It is.
Kill it. Oh, man.
No, and of course, you guys are not going to remember this, right?
Of course.
But when you get to organic, this becomes something very important. And then in organic, guess what I have to do? Explain it again. So I draw my little unforgettable picture. See? This one versus this one.
No doubt.
When I get tired,
You just
what?
repeat the topic.
I don't get tired. I love drawing it.
You enjoy it.
I do. Okay? That is, that type of bonding is for covalent bonding, okay? That's called, that's the amount of energy required to break covalent bonds is called bond dissociation energy, BDE. The amount of energy required to break a covalent bond is called bond dissociation energy, and it increases or decreases how I explained.
Bond dissociation energy.
You want to sit next to me? I think you'll hear me better.
No, then you talk
BD.
about
Bond dissociation.
Because you,
No, but I spelled it wrong, so I just put como que. I'm serious, I spelled it all wrong.
You see,
Guys?
none of us.
look. What I need for you to do is not try to write every word I say. I need for you to
Understand
hear
the
what I
concept.
say. It goes inside of your brain. You process the information, then you write it down. Okay? I'm gonna say it. Nobody write anything down. Look here only. I'm gonna say it. Try to pay attention. She won't be able to, but everybody else can. You pay attention, and then you write it down. Ready? I forgot what I was gonna say. Yeah, I'm gonna say it. Bond dissociation. Don't write it down.
Ah, dang.
Bond dissociation energy
Oh, bond.
refers to the amount of energy required to break covalent bonds.
Bond association.
No. If you have an attention deficit, you got two choices, either Ritalin or okay, I'm gonna say it again.
All I picked up was energy
Bond
required to break
dissociation energy.
Well, we all have short-term.
Bond dissociation energy
covalent. Oh, bond dissociation.
is the amount of energy required. Amount of energy required is not important, yes?
Of course.
You picture it. Bond dissociation energy is the amount of energy required to do this, look. Break. That's called BDE. I don't even know what the problem is.
And that has to do with that 0.4, 0.0 thing?
Huh?
That has to do with the 0.0 to 0.4 thing?
No, that has to, that 0.4 thing has to do with bond polarity. Bond energy is bond size. You missed it. You guys are not paying attention. You guys are playing around. Okay? Now the energy required to break the attraction between ions, which is different from covalent bonds. Should it be called bond dissociation energy? No. It's called
Ion.
bond enthalpy or lattice enthalpy. Lattice. Do you know how to spell lattice?
LATTICE.
Right?
Oh, nah. There you go.
That's a girl's name, right?
Lattice.
Sounds good to me.
That sounds like lettuce. Lechuga, would you name your child lechuga?
Well, would you name your child Navy?
U.S. Navy, have you heard that? Usnavi?
Whose name? We have heard it.
Usnavi.
Let me tell you, those people from that country have okay, that's called lattice energy. And once again, it has to do with size, and it also has to do with charge. Bond dissociation energy has to do with size. Yes,
Lattice energy is the energy required to break the attraction.
between, yeah. So, here it is. Sodium fluoride and potassium fluoride. Both of them have both of these are ionic, yes. It has a positive charge, negative charge, negative charge. This is not called bond dissociation energy. This is called lattice energy. Which one of those two will have a higher lattice energy? Meaning, which one will require more energy to break?
Whichever
You
one's
should
the bigger
already know it,
size.
it's the same.
Yeah. Whichever one's the bigger size, huh?
They're both
The atomic size?
No.
Okay? Okay.
Potassium chloride?
Guys, listen. Okay, maybe I don't know if I said this wrong last time. Which bond here is weaker? Which of those two bonds has a lower bond dissociation energy? Which one of those two has a lower bond dissociation? Yeah, because it is the weakest, because it is the biggest. But that one has the highest bond dissociation energy, yes or no? I'm asking here, which of these two has a higher lattice energy?
Higher sodium chloride.
Okay, yes. Potassium is bigger than sodium. So this one is smaller, this one has a higher lattice energy. How do you like that? And it is once again based on size. And then there is something that happens if you got ions that are higher than, this is +1 and this is +1, yes? But if you have calcium oxide, CaO, what is the charge on calcium?
2 plus.
2 plus.
2 minus.
+2 and 2 minus oxidation, no, it's the same, okay? I should say 2 plus. Okay, so the force of attraction of charged ions, if the charge increases, the force of attraction increases. So this, because it has a +2 or a 2 minus and a 2 plus, has stronger attraction than a +1 and a -1. Okay? +2, -2, more attraction than +1, -1. How is the force of attraction between those? SC. Try to find SC in the periodic table.
It's pretty weak.
What's this element? Scandinavia?
Scandium. Scandium.
What's the charge of this?
4 more.
Minus 3.
This one?
Will be +3.
3 plus.
So, the force of attraction between those two, guess how much it is?
Stronger than the calcium.
Stronger than the calcium oxide. This is about 7,000 kilojoules of energy to break that thing. You know what 7,000 kilojoules is?
No.
Long.
You cannot imagine the strength of this. Okay, very, very strong. The thing never wants to melt, ever. Okay, so the higher the charges, the stronger the force of attraction between them. Okay, regardless of the size. This will be stronger than that, which is eventually stronger than that. Now on the test, what can I give you? I can give you one that is +2, -2, like this one here, and ask you to compare one that is with the +3. So I can give you something with +1, something with +2, and something with +3. And ask you which one would have the strongest attraction or the highest lattice.
Okay, so it's +2.
The one with the +3, which should have next to it a -3. I won't give you something that is like CO2. Okay? Yes or no?
Yep.
Which of those bonds is more polar? Which of those bonds is
HCl. HCl.
What?
HCl.
What?
Oh.
Calculate the difference in electronegativity.
It's HO.
Hello?
Oxygen has a higher.
Yeah, this one, 100% guaranteed. This has a higher electronegativity difference, so this is the more polar bond. So which of those bonds is the more polar? This one is the most polar bond.
1.3.
Because oxygen has an electronegativity of 3.5. And the difference between 3.5 and 2.1 is greater than the other two, which are 3.0, both of them. Okay? Those are test questions.
Okay.
Of course, if the bonds are polar, there is a possibility that the molecule will be polar. If the bonds are non-polar, then the molecule will be non-polar. But that has something to do with the shape of the molecule. Okay? Do you guys want to do molecular shapes?
Yes.
In order for us to do molecular shapes, we have to know how to do Okay, let's calculate something called formal charge. Once again, you will see formal charge again in organic chemistry. Okay? Now this formal charge thing is a complicated thing to, not complicated, it's not so complicated, but it could be. Okay? So for example, if I want to know the formal charge on the hydrogen and on the oxygen, meaning it's a charge now. Hello, is a charge? Do you see a charge?
No, I don't see a charge.
No, you don't see a charge. But we are going to calculate the charge that it has because it does have one. But that's a Lewis dot structure, that is the correct Lewis dot structure, which you get to from what we did last time. Yes, you remember how we did it?
It shows the fingertip.
How do you know about that?
It shows me.
Made show you the thing?
Yeah.
Is that really correct?
What?
I thought O can only have 6. I thought oxygen only had 6 grams of oxygen.
So what?
Air has 7.
7.
Is that 8?
8.
My friends, a bond, this line, it's okay if you don't know, okay?
It's 2 electrons.
You're not the only one. This bond, a bond, and this is called a bond. Okay, maybe I didn't explain this before. A bond is composed of 2 electrons.
2 electrons,
Yes.
yes.
So that line there is 2 electrons. Do these 2 electrons belong to oxygen?
Yes.
Do these 2 electrons
They share.
belong to hydrogen? They share. They're sharing
They're
them.
sharing.
So these 2 are on the oxygen as much as they are on the hydrogen. It's called sharing. Girls don't know about this type of stuff. So, here's what we're going to do. We're going to call the valence number of electrons, and like he said, I'm going to teach you the finger trick. You like the finger trick?
Uh-oh.
I'm sorry, isn't hydrogen plus 1? It's not ionic bonding. my
It's
friends.
molecular. It's covalent.
It's not plus, it's not minus. They're being shared. Okay? The difference in electronegativity between these two is what's the difference in electronegativity?
0.9.
Oh, it's not 3.0, huh?
3.5.
What's the
1.4.
difference? 1.4 belongs to what? 1.4 belongs to polar covalent. This is not positive, this is not negative. Yes? This has a delta negative, and this has a delta positive. They are not positive. Now the oxidation number of H is +1 in that case, but that's different. Let's not go crazy, okay? So, different things are different. Okay, so this bond is called polar covalent. Yes? This bond is polar covalent. And because it's polar covalent composed of two nonmetals, this bond is covalent. Electrons are being shared. We can calculate the formal charge. The formal charge is the charge that the OH has, right? Okay? And like I said, I'm going to teach you the finger trick, yes? The finger trick is valence number of electrons. I want to calculate it for hydrogen. Minus the electron it has according to your finger. And you count the bond as 1, right? Because you go like this, 1. But each of these electrons, because they're placed differently, you count them with your finger. Yes? I'm going to demonstrate. Valence number of electrons for hydrogen, how many? 1. And I go, whatever bond or electron pairs it has, I have to count it with my finger. I am going to go, how many is this? 1. So 1 minus whatever I count with my finger is 0. Formal charge on hydrogen is 0. Okay? You didn't get it. You never do. So, what's the valence number of electrons? Guys, valence number of electrons for this one? 6. I am going to count with my finger the electrons that belong to oxygen. Yes? For each bond, it's not 2 that belong to it because they're shared. 1 belongs to oxygen. 1, 2, 3, 4, 5, 6, and 7. 6 minus 7 gives you? Minus 1. So the formal charge on that oxygen is minus 1. Let's practice some more, right?
Yes.
Calculate the formal charge on nitrogen. Okay, let's do it. I don't know why it's taking so long. I understand her, but the rest of you I don't. So, how many valence electrons?
5. Nitrogen.
Nitrogen, right? You talking about?
How many valence electrons does nitrogen have? How do you know it's 5? Because?
Because you count how many it has.
Valence electrons. How many valence electrons does nitrogen have? 5, you said. Why is it 5?
Because it has 3 bonds.
Because it is in group 5. Valence number of electrons has nothing to do with what you count at all. Valence number of electrons comes from the fact that nitrogen is in group 5 of the periodic table. Yes or no?
Yes.
And now, I am going to count with my fingers, subtract whatever electrons it has. 1, 2, 3, 4, and 5.
0.
0. This nitrogen is neutral. Yes? And of course you know that because nitrogen makes how many bonds? 3 bonds. And it has 3 bonds. It's not charged. That nitrogen has 4 bonds. Calculate the formal charge on the nitrogen.
1.
1.
Once again, what's the number of valence electron nitrogen has? 5. Why does it have 5?
It's in group 5.
Outstanding. I love it. And now what do we do next?
We count.
With
count.
what?
The fingertip.
Okay. 1, 2, 3, and 4. What's the formal charge here?
1.
Plus 1. So that nitrogen is plus 1. Nitrogen has a positive charge. Let's continue, right? Do you want the real equation? No. You like the real equation? Let's see what you like more.
I don't think it's like super long.
Who's blowing up, man?
It's not half first.
Huh? Can you tell your girlfriend that not to bother you during class, man? The girls are. Did you know that only the female mosquitoes bite, that the male mosquitoes don't bite? You didn't know that? I'm telling you, girls have been sucking on my blood for a long time. All right, let's do this one. How many valence electrons does nitrogen have?
5.
Minus the ones I count with a finger.
6.
1, 2, 3, 4, 5, 6.
Minus 1.
Minus 1. So the formal charge of that nitrogen is minus.
So Professor, what if one of those had a charge already on it? Or?
Huh? It can't have a charge because you're trying to find it.
Okay, yeah, but what if it did have one? And then can you
It
still?
can't have one because if it has one, then
Oh, it's already calculated for you already?
you have. This is you calculating the charge. The charges that I was giving you before, like this, for example. Oh, you have to know that NO3 has a minus charge.
Right.
That's what you can do now.
Oh, okay.
You can calculate this formal charge now.
Oh, okay, I understand. Okay.
Okay? If I give you the structure, and we're working our way towards that, okay?
Okay.
But we can't build the structure on our own, right?
Of course you can.
Plus what?
So that's my question. If oxygen has 6 valence electrons and hydrogen on this periodic table is in group 1, so it only has just 1, how is a bond 2? Is that 1 like bouncing back and forth, so you count it as 2, or I don't get it?
The two electrons are going back and forth.
It's only 1 electron.
No,
It's 2.
electrons.
One from the oxygen and one from the hydrogen. They are sharing it.
That's cool.
So in this
So
reaction,
there's a total
nitrogen
of 7,
plus 5?
but there's still
There is not 7. There is 7 from the, there is 6 from the oxygen, yes?
1 from the hydrogen.
And 1 from the hydrogen in that case. But the oxygen had 8. You're asking where did the other one come from?
Yeah. It's like when we need to draw it, we need to be able to know that there's 8 total.
Yeah, of course. But then I drew it for you.
But you said that we could draw it on our own. We can't.
And not yet.
No. All right.
Not yet. In that case, you could not draw it. No. If you're asking, if I ask you to draw this, you cannot draw this without me saying to you that. You can't draw it. But that's not what we're doing here. What we're doing here is finding out what the formal charge is when I have already drawn it for you. Okay, last one. Let's do a couple of these, and that's it. Let's call that a day. Oh no, you guys wanted the real equation, yes?
No.
She wants the real equation.
No.
You don't like the figure, do you? No, you don't like it. Do you like it?
You don't want that really.
You don't want it? Alright, I'm gonna show you. This is the real equation. Valence. You tell me what you like the most, okay?
Anybody want to bet you'll like finger trick most?
Everybody likes the
No,
thing.
no,
want some bets?
Let's show them, okay? They gotta feel the whole thing.
All right.
Valence, okay? Valence number of electrons minus lone pair electrons minus bonding electrons divided by 2. I told you. What do you like better? I told you. I mean, this has been studied in details by me. Okay. You always like the finger more. Okay. But this is the same. Okay. Valence. Let's say for carbon, how many valence electrons does it have? Carbon has 4, yes? Minus lone pairs. Does it have any lone pair electrons?
No.
So if it's not lone pairs, it's lone pair electrons. Yes?
Lone pair, which is
So how many lone pairs
Yeah.
electrons does it have? 0. Minus bonding electrons. There is 2 here, there is 2 here, and 2 here. There is 2, 4, 6, yes? So 6 divided by 2 is 3. So 4 minus 3 is plus 1. Okay? But in my opinion, but that's just me. In my opinion, 4 minus 1, 2, 3 is better, yes?
Yes.
I think it's better. I'm not sure. But I think that's better. Yes? So let's do it the long way for this one. So valence electrons is 4 minus lone pair electrons, which is 2, minus 1, not 1, 2, 4, 6.
6 divided by 2.
So how much is this?
Minus 5.
Minus 1. If you would have done this my way, yes? If you would have done this my way, you would have said 4 minus 1, 2, 3, 4, 5. I don't know, you can do it whatever way you want. It's gonna come up again, okay? When you take organic, you are going to do this so fast without even calculating the stuff. Now, what time is this class over?
12:30.
We gotta have.
What do you think? Just guess.
2 minutes.
Okay, all right, let's, you wanna do some Lewis-Dot structures? Let's do the foul-smelling SO2. Like when something dies and smells like rotten eggs, that's SO2.
I'm sorry. I didn't hear. Okay, the same. Gracias, thank you.
Okay, how do we do this? SO2, valence number of electrons for sulfur.
6. Oh,
You,
2.
6.
why don't you have a periodic table outside?
I do.
Your friend has one and you,
No.
6 because it is?
Okay, group 6.
All right. Sulfur is in group 6 because everyone has a periodic table. Yes, that's how you know. It's in group 6, so 6 valence electrons. Oxygen is in group 6. 6 valence electrons times 2, this is 12. Plus the 6 from before, this is 18 electrons I must place here. I am going to choose the central atom. Which do you think is going to be the central atom?
Sulfur.
Sulfur is going to be the central atom. It's the one that is in the lowest quantity, right? And makes a good amount of bonds, right? Sulfur is the middle. And I'm going to make single bonds, the rule, that's what the rule says. Single bonds to the other elements, oxygen and oxygen. Yes? That's the rule, yes or no?
Yeah.
The other rule is that now you, on the outside electron, on the outside elements, you gotta fulfill the octet rule. So you gotta put 8 electrons on it. There you go. Yes or no?
Yes.
That's 2, 4, 6, and this is 8. So far, I have 8 electrons here, 8 electrons there. That adds up to 16 electrons. Yes or no? I need how many? 18 electrons. Whenever I have electrons remaining, I am going to place them in the central atom. There they are. Yes? So now, we look. This sulfur here, this is the third group of the periodic and the third period of the table. Yes, of the periodic table. Because they are on the third period, guys. Because they are on the third period, it can expand the octet. Write it down. Elements in the third period and below, yes? can expand their octet, so they can violate the octet rule. It doesn't mean it's always violated. The ones that are never violated is in the second period. But the ones in the third can violate the rule. Yes?
Yep, right.
So, is the oxygen happy here
Yes.
with 2 bonds only? Let's calculate the formal charge for this oxygen. What is it?
It's 6 valence, and then you gotta count with the finger.
6, 1, 2, 3, 4, 5, 6, 7.
Minus one.
Minus 1.
Minus 1, and this is?
Minus
Minus 1. And the sulfur in the middle is?
6 minus, and then
8.
you,
Four
6 minus 4.
plus two.
So it's plus
6
2.
minus
Plus
4.
1, 2, 3, 4.
Plus
What is it?
2.
Plus 2. Now write this down. This is called the resonance structures.
Resident?
Resonance.
Resonance.
Resonance. Look here. Resonance. Resonance structures are always better with the lowest number of formal charges. Okay, so in general, you want to have a good resonance structure has the lowest possible number of formal charges. Okay, obviously you want to have resonance structures in which the elements make the number of bonds you predict. Yes, oxygen, for example, makes how many bonds?
6.
Oh,
Oxygen is
Oxygen?
two.
it has 6 valence electrons, but it does not make 6 bonds unless you are in what field of study. Now just don't say it, okay? It's going to be recorded. Oxygen has 6 valence, but from 6 to get to 8 is 2. It makes how many bonds, oxygen?
1
It makes 2 bonds. So what we are going to do is we're going to draw oxygen with 2 bonds. And this is called resonance, yes? What happens is these 2 electron pairs go to make a double bond between the oxygen and the sulfur. And it's going to now look like this. Okay? And now it happens on the other side again. Please calculate the formal charges again.
So you give sulfur the maximum amount because it's in that series, right? It just rather be that way.
But Professor,
It
is
can be anything you want it to.
yeah, I was just gonna say, either way is correct, either way, on the whatever structure? No?
No.
Oh, no?
Either way, it's not correct. I mean,
Oh,
yeah, it's kind of okay, but it's not.
oh, okay.
So, you mean either way from here and here?
Yeah.
Yeah,
Okay.
on the structure
No,
part, yeah.
It's not. What's the formal charge on this oxygen?
0.
0. What's the formal charge on this oxygen?
0.
What's the formal charge on this sulfur?
0.
I don't know, 6 minus 1, 2, 3, 4, 5? It's 0.
0.
This molecule there is not charged. And SO2 is a charge? I don't see a charge there. Do you see one?
No.
I don't see it. So it's not charged. So is this a better, and of course, these minus 2 charges cancel with a positive 2, yes? They
Right.
do cancel out. So this was correct. But this has a large formal charge separation, yes? You have a lot of formal charges, so which one is a better resonance structure? This is a better resonance structure because it has no separation of formal charge. So that is how SO2 looks like. Yes or no? Now, how many regions of electron density does the sulfur have? You never heard of that before. I gotta, get you going first, you know? You guys have issues.
Professor, what did you say that has a better formal structure because of what?
Yes,
There's no
it has that
separation
formal
of
charge.
formal charge.
This has -1 plus 2 -1. That's a lot of formal charges. This one doesn't have it. So, how many regions of electron density? Look, this is a region of electron density. Do you see electrons there, yes or no?
Yes.
But these two are in the same direction, you can say, yes? You see both of them are going that way. So this is another region of electron density, and here is another region. How many regions does that have?
3.
3. Okay? We will talk about more of that later.
That's how you get the molecular, right? The molecular structure?
Those are technically.
The molecular geometry of
What?
it?
That the electrons are like oxygen.
Yeah. The orbitals are there. They're called hybridized orbitals, which we're going to talk about hybridization later. Molecular orbital theory, a little bit. Okay, let's do another one. How about that? You want another one?
Yes.
There you go, CO2. Actually, while you're on it, no CO3 with a 2 minus. And of course, if it has a minus, what do you do to electrons? For every minus, you are going to add, no.
You add them.
For every minus, you add 1, yes?
Yep.
Hello?
Yes.
Hello?
Yes.
Okay. Carbon, how many valence electrons? 4. Oxygen, 6 times 2 is 12 plus 4, 16 valence electrons. There it is, carbon. I'm going to make single bonds to the other ones, and I am going to do what? Add electrons until the ones outside fulfill the octet rule.
Right.
Okay, I'm going to do formal charges next. The formal charge on this oxygen is minus. Formal charge on this oxygen is minus, and the formal charge on the carbon is 4 minus 1, 2. Formal charge here is plus 2. Once again, that cannot be like that. Yes? That is not a good resonance structure. So what do I have to do? I have to make double bonds somewhere. Okay? Because the oxygen wants to have how many bonds? 2. And the carbon wants to have how many bonds? Guys, what's the deal?
4.
Oxygen is in group 6, it wants to make 2 bonds. Carbon is in group 4, it wants to make 4 bonds. Nitrogen is in group 5, it wants to make
3.
Okay. The point is to get to 8. Okay? In group 4, how many do you need to get to 8? 4 electrons, that's 4 bonds. Okay? In group 5, how many do you need to get to 8? 3 electrons, that's 4 bonds. Yes? It's 3 bonds. 6 electrons, how many? To get to 8? 2 bonds. And 7, how many? 1 bond. Is that clear? Let's put an end to this one. So, what am I going to do? I'm going to make double bonds here. This electron pair is going to make a double bond here. I am going to make a double bond there. You see, those 2 electron pairs get used up in the double bond. So, here it is. I am going to do it on both sides. Calculate the formal charges again. It is neutral. Everybody's neutral. Tell me, how many regions of electron density does that have? It has 2. This double bond here is 1 region of electron density. This double bond is another region of electron density. It has 2. Let's do CO3. What's CO3? Carbon is how many? 4. Oxygen is how many? 6 times 3. 6 times 3 is 19. 18. So,
Plus 4 plus 2.
and I have 2 electrons here I need to add, yes? Plus 2. So this is 18 plus 2 plus 4 is
24.
24 electrons I need to place, yes?
Yes.
Now I needed to give you this charge, yes? If I don't give you this charge, you'll have a problem, yes?
That'll be all thrown off, yeah.
Single bonds to everybody. There you go. Does it look good? Single bonds to all oxygens. You like that? And now what? Hello?
We fulfill the
Fulfill the
oxygen.
octet rules for the one outside.
Yeah, it's gonna be
And now I recount. How many?
20
Excuse me?
24.
There is 8 here, and 8 and 8. Snap. That's 24 electrons. I cannot place any more electrons on this thing. Formal charge here on this carbonate, on this oxygen is -1. Here -1 on this carbon, +1. That is not good. So what am I going to do? You are going to do double bonds. The carbon wants to make how many bonds? 4 bonds, okay? So what is it going to do? One of these electron pairs is going to go in there, and it is going to form a double bond. What? So, how is this going to look? This is going to look like this. Here's the carbon, an oxygen there, and another oxygen here. Yes? What's the formal charge here? On this oxygen? 0.
0.
What's the formal charge on this carbon? 0. What's the formal charge here? Minus. What's the formal charge here? Minus. How many minuses?
2.
2 minuses. This is why this is called CO3, 2 minus. And that's how it looks. How do you like that? You love it,
You
don't you?
can use whichever oxygen or it just has to be carbon.
Yeah, that's what we are going to do right this second. So there is a possibility, since she asked, that I could have done it in another one of these oxygens, okay? And this is called, when we move the charges, we are making new resonance structures for this. The resonance structures can be good or bad. Whenever we have resonance structures, we are going to draw these arrows that are pointing towards both sides. Guys, do we have another test here to take?
Yeah.
Test next week. Outstanding.
What day?
Thursday.
Thursday?
Sorry, you are coming to school to take exams. Yes.
So when? Thursday?
Bless you.
What did you have in your ears when I said test next week on Thursday?
My secret. You wanna know it?
Yeah.
Really? I don't think
What do you
about
want on the test? What do you guys want on the test?
Resonance structures, the
The
periodic trend.
Nothing that was in that PowerPoint.
No, all of that is gonna be on it.
What's gonna be refraction,
All
diffraction?
six
I talked about all of this, brother, on the board.
But the problems,
The problems are silly, man. You know when I'm gonna do a problem with multiplying H times V? What explanation is there? Look, calculate the energy for this frequency, H times V. You get this number multiplied by this number. I gave you this number, I gave you this number. It's on the PowerPoint. Yeah, you're gonna have it, okay?
Why can't we have it like not next Tuesday, but the following?
because it was the final,
No
yeah.
more time.
Okay, guys, look.
It's a time crunch thing.
Yeah, I have to go fast through things, okay? I have to go fast through this. I have to go fast through most of it because at the beginning of the semester, I gave you time for you guys to get used to things, okay? And for you guys to get used to me and to start building, yes? And now we are already at a high level of, yes, of understanding. I teach less, you learn more. What do you want on the exam next week? We're gonna have light. We're gonna have refraction, diffraction. We're gonna have calculating the energy of this light. We're gonna have the Rydberg constant. The Rydberg equation. We're gonna have the de Broglie wavelength.
Professor, what could be possible questions for diffraction, refraction?
Uh-huh.
Like
It's like
that, like what that is.
Conceptual stuff.
Yeah,
The
yeah,
definition.
what it is done.
The definition.
Yeah.
Oh, okay.
and the definition what it leads to. Okay, like for example, what nature of light is diffraction? Is it the wave-like or is it the particle-like nature of light? It is a wave-like. Okay? That's okay, you haven't done anything. You haven't been studying for my class. That's the problem.
No, we.
You think this information get into your head. When that day came, you knew it all. When I did it in class, you knew it. I said, what are the examples of the wave-like nature of light? And that was, what was it? Diffraction, refraction. What was the particle-like nature of light? Tell me those examples. Black body radiation, photoelectric effect, and atomic spectrum. Okay, so apparently I did not do a good job on the other one, right? Let's blame that on me, it's my bad. Yes, you're gonna calculate the energy if I give you a wavelength. You have to know what constructive interference is, you have to know what destructive interference is.
Just definition?
Yeah, definitions, because that's what they are.
Yeah,
Okay.
The only math problems in that chapter are de Broglie wavelength, which I'm gonna give you. I'm gonna give you the mass of the object and the speed of the object, yes? That's all you need. And I'm gonna give you the constant too. I'm gonna give you to calculate the Rydberg and maybe, you know, maybe not, probably. I don't know.
What about Mansell?
Who? Yeah, that's the next chapter, yes? Electron configuration, blah, blah, blah. Yeah, that's on it.
And when can we start watching the videos?
What?
Quantum number?
Oh, by the way, I haven't said, guys, that the videos are
No,
online.
no, you haven't said or asked in the link yet.
No?
Oh, damn. The videos have been online since the long time. You seen them or not?
Oh, wow.
Okay, this one you search. This one you search for. Okay, ready?
Pedro Garcia.
Yeah, actually, you can search for Pedro Garcia chemistry. Okay.
Okay.
If not, it's not gonna come out. But you search for P Garcia 933. Okay, and you gotta read what it is because I've been putting some videos for organic. You don't want to do those, okay?
We put that on YouTube?
Yeah.
Yeah.
You haven't uploaded 5 days.
I uploaded it what?
You haven't uploaded in like 5 days.
Yeah, I didn't upload the last class. I uploaded on the weekend. Organic videos and the videos for this class last week. Okay, so you search for it, they're there. You gotta look for stuff that is related to your class, yes? Which to some of you is gonna be like, oh, which one is it, Professor? I don't know. Electron configuration, or should I do elimination reactions? Which one? Electron configuration, yes? What else is on that test? Yeah,
Quantum number?
quantum numbers, off-flow principle, violations to electron configuration.
Electron affinity,
All the trends, all the trends, bond strength, what we did today is gonna be on the test too. Okay?
so Professor, the final is like a massive of everything, right?
The final is everything together.
Yeah.
It's the end of the world type of thing.
Dang.
We're not done, I gotta finish this, yes.
Well, I was gonna ask you about.
Yeah, so, this is how resonance is, okay? I want you to look, I don't want you to write. Look, this oxygen here can go, hey, I want to make a double bond to you, carbon. And the carbon, since she doesn't care too much, she goes, hey, your electrons out. And the electrons go that way. And with the resonance structure that is now formed, there's a double bond to this oxygen here on the top, yes? 2 electrons now make a double bond, yes? The electrons that were making this double bond came outside, and now this oxygen has a negative formal charge, and this one here on the side with another formal charge. Does that look like this?
Yes.
Yeah.
Yes, but with a different oxygen, yes? And now she goes, okay, let's do it with this one too, a piece for everybody. So, then, this is what happens. What happens? The 2 electrons from here go and now make a double bond there. But carbon cannot make 5 bonds, yes? So these 2 electrons from here have to go outside. So these 2 electrons go like that. You gotta draw them like I am showing you here. And now this oxygen has a minus charge. This oxygen has a minus charge. And now this one is the one that has the double bond. Those structures, write it down, those structures are the same. Resonance structures do not exist. Write it down. What exists is a hybrid between all of them. So resonance structures are not real, okay? Like what I drew there is not really what it is. It's a mix of all of them. They're happening so fast that it looks, I don't want to draw how it looks.
So how many regions? We got 3.
Here you would have 3 regions of electron density, yes? How many regions here, guys?
Hybrids.
1 region here, 1 region here, 1 region there. That's for next week, okay?
Called region of electrons.
Electron density. It's called electron geometry domain. Okay? Up to now is what you have on the test, okay? Yes, and the test will be Thursday of next week. You can ask me questions. I will continue this topic next week. Okay, my friends.